The human cerebrum is one of the savviest on Earth. However, there are a few things we can't really understand. One of those is the catch-22. We've developed to consider reality with a certain goal in mind, but there are catch-22s out there that suggest reality doesn't work the way we think it does. Now, some physicists think they've solved a 50-year-old mystery, but have they? And what are the other most bizarre catch-22s? Prepare to find out. A great deal of you are probably familiar with the Fermi catch-22, named after Italian physicist Enrico Fermi, who is famous for making the first atomic reactor. This oddity looks to answer the question, where are the aliens? Given that our star and Earth are part of a relatively young planetary system compared to the rest of the universe, and that it's possible for a civilization to achieve interstellar travel during this time, it seems we should have been visited by some form of extraterrestrial intelligence by now. Now, some say it's not a real oddity because we can figure that there is intelligent life out there. But the Drake equation, used in this supposed conundrum, measures the number of potential civilizations in our galaxy. The Drake equation uses 7 factors to estimate the number of recognizable civilizations in the Milky Way. This gave us an idea that there could be millions of Earth-like planets with civilizations out there. But this was back in 1961, and no one knew of any planets orbiting stars other than our own. It was only recently in 2020 that astronomers, using data from the Kepler Space Telescope, found that there are over 300 million planets with similar conditions to Earth throughout the Milky Way. The study concluded that approximately half of the Sun-like stars in our galaxy have rocky planets in habitable zones where liquid water could exist on the surface. In fact, planets are very common and outnumber stars in our galaxy. Very soon, the James Webb Space Telescope will be going into space to search for new potentially habitable planets. We'll have another video on that soon, so be sure to stay tuned here. Since it is now so obvious how many universes are out there and how many possibilities there could be for extraordinary civilizations, the question remains, why is the universe silent? Perhaps we'll find out soon as technology advances, or maybe we've already been visited by some distant civilization and just don't know it yet. There have been many unexplained UFO sightings recently, and some believe extraterrestrials are already here. Strong evidence of that would stop this oddity. The bootstrap catch-22 is a conundrum of time travel that questions how something that is taken from the future and put in the past could ever appear. It's a common theme used by writers to inspire plotlines in many sci-fi movies like the Bill and Ted films, The Terminator and Doctor Who. So, let's take a look at one of the examples of this oddity. Imagine you're a person who goes back and forth through time, but before you go on a grand adventure, you go into a bookstore and buy a copy of Hamlet written by Shakespeare. You then, at that point, turn back the clock to London during the Elizabethan era and give the book to Shakespeare. William S. then copies the book and claims it as his own work. Hundreds of years go by, and during this time Hamlet is printed and copied many times, until a copy ends up in the very bookstore where you got it from. The question then becomes, who wrote Hamlet? This is another popular mystery which involves you traveling back into the past to take out your granddad, we mean deleting his reality. Now, we know everyone here loves their grandparents, but this is just a model. In this scenario, you're a person who jumps through time, and you pop back so as to carry out the act and eradicate your granddad's presence. You then return to present time, but here's the thing. With your granddad gone, your dad wasn't born, and you now realize you never even existed. Everything about you has now been eradicated, including all your family, friends, possessions, and history. So, you could never have been born in the first place. By doing this, you have now created an alternate timeline or even entered a parallel universe. By the way, for those who missed our video on parallel universes, check out the link in the description. Another interesting variation of the granddad paradox is traveling back into the past to dispose of Hitler to stop World War II. This would make for some interesting results. Suppose you have a shiny time machine, and you have a plan to return before things got out of hand during the war and put things right. The problem now is that the action eliminates any reason to turn back the clock, along with any knowledge that the reason to time travel back ever existed. Acting as a time-traveling killer essentially creates an oddity. Along with the many worlds theory, going back in time could create a new timeline without de Fura, but the old timeline would still exist. You could even create a new timeline that's worse than the original one. But what would happen if you sent something back through a wormhole? The red sky catch-22, Among all the stars in the Milky Way, 80% are red dwarfs or M-type stars, which according to researchers' calculations could keep burning for trillions of years. The Sun, for example, will burn for about 5 billion years. So it's not surprising that there are now more red dwarfs than any other star. With so many red dwarfs out there, our night sky should be dominated by their light, and at least some of them should have planets suitable for life. So where are the red dwarfs and why haven't we found life in their systems yet? This is the Red Sky Catch-22, proposed by cosmologist David Kipping from Columbia University. The way we view stars in space is different from what we would see through Earth's atmosphere. The Sun appears white, massive, hot stars look a bit blue, and cooler stars appear either white or orange. Red dwarfs are faint to such an extent that even the closest star, Proxima Centauri, can't be seen with the unaided eye. In telescope images, such stars can have various colors depending on the filters used, but the red sky paradox doesn't have anything to do with the color of the universe. It's related to the search for extraterrestrial life. The idea is that planets in red dwarf systems have the best chance of harboring life because these stars burn for much longer, and there are so many of them. Around 15% of red stars have Earth-sized rocky planets orbiting them, and many of these exoplanets are found very close to their stars, which means they get plenty of light and heat. This also implies that liquid water could exist on these planets. However, life as we know it only thrives on Earth, which orbits a yellow dwarf star. Yellow dwarfs make up only a small fraction of the stars in our galaxy. So, does this mean our star is special? Well, not exactly. The Copernican principle states that there are no privileged or unique regions in the universe. In other words, our place in the universe is ordinary, but that doesn't mean life is ordinary throughout the universe. There might be an answer to this so-called oddity. Red dwarfs could be more dangerous to surrounding planets by flooding them with harmful radiation. These stars' gravitational forces are so strong that planets can become tidally locked to them, turning one side into a scorching hell while the other side remains cold and frozen. Planets in red dwarf systems also lack protection from objects coming from space. Open NASA's catalog and search for gas giants close to red dwarf stars. They are very interesting, and giants like Jupiter often act as a kind of space shield. They interact with comets, asteroids, and other celestial bodies that can destroy or severely damage rocky planets. This, according to Kipping, makes life much less likely to form in red dwarf systems than in yellow dwarf systems. Space is full of fascinating stars, and one of them threatens to disrupt the accepted image of the universe. The late great Joseph Polsinski, the famous theoretical physicist who wrote the book on string theory, also devised a mind-boggling scenario involving a billiard ball sent through a wormhole. The ball travels back in time, eventually hitting its past self and preventing it from ever entering the wormhole. Some physics students have thought of solutions to avoid these paradoxes, where the ball would come out of the future at a different point than the one used to create the Catch-22 and deliver its younger self. Looking below, rather than thumping it totally away from the wormhole, a blow shifts its direction in the correct manner, so it will turn back the clock with the point expected to deliver it to its younger self. This looking blow, now here's something that will make you contemplate reality differently, describes the Catch-22 of the oldest star, HD 140283. The star, located in a cluster of stars in Libra around 190 light-years from Earth, puzzled astronomers when they first determined its age using the Hipparcos telescope. They discovered that the star moves at 1.3 million kilometers per hour. However, what astonished cosmologists most was the star's age, which was initially estimated to be around 16 billion years. This result seemed very peculiar to scientists, given that the age of the universe itself is only 13.8 billion years. So they decided to investigate further. After 8 years, with the help of the Hubble telescope, astronomers conducted studies using parallax spectroscopy, photometry, and star glow. They concluded that HD 140283, according to new measurements, is 14.5 billion years old. However, because it is incredibly difficult to measure the star's distance and luminosity, there's an uncertainty of about 800 million years. It is likely the star could be 13.7 billion years old, meaning only slightly younger than the universe. But what about the star that is much closer to us? The observer's mystery is indeed an odd one. Of all the strange facts in quantum theory, Few are stranger than Schrödinger's famous tale about a cat that is neither alive nor dead. For the record, this is a thought experiment, and no animals have ever been harmed. The conundrum describes a cat locked inside a sealed box with some radioactive material, a Geiger counter, a hammer, and a vial of poison. The radioactive material has a 50% chance of decaying. If the Geiger counter detects radiation, it triggers the hammer, which smashes the vial of poison, killing the cat. However, you wouldn't know whether the cat is alive or dead until you open the box. So, until the box is opened, the cat is both alive and dead at the same time. How is this possible, you ask? This is because simply observing the system changes the outcome of what happens to it. You can't know something is there unless you see it. Now you're probably saying this is all very weird, but consider another observer's oddity: the double-slit experiment. This is the most famous physics experiment ever. Imagine a wall with two slits in it, then throw tennis balls at the wall. Some will bounce off, but some will pass through the slits. If there is a wall behind the first one, some of the tennis balls that made it through will hit it. If you mark where the tennis balls hit the second wall, you would expect to see two sets of marks, one for each slit. Sounds pretty straightforward, right? But in the double-slit experiment, something incredibly bizarre happens. When you shine a light through the slits, light isn't just a wave, it's also a particle called a photon. Now, if you shoot a single photon at the double slit, it creates an interference pattern on the back wall as if it's interfering with itself, as though the photon passed through both slits at the same time. But here's where it gets even more interesting. If you observe the double-slit experiment, the behavior of the photons changes, as though the photons are alive and aware that you are watching them. We know this because if the experimenter tries to figure out which slit the photon passed through, the interference pattern disappears entirely. Simply observing the photon seems to change the events that have already occurred. How is this possible? No one has figured it out yet, but maybe you will be the one to solve this riddle. The weak young child Catch-22, according to the standard model of solar evolution, states that billions of years ago, the sun radiated about 30% less energy than it does today, with less energy reaching the planet. Space experts say that Earth should have been frozen solid during those early times. Yet some researchers think this isn't what happened. Climate models of the Earth during the Archean age, 4 to 2.5 billion years ago, suggest that the Earth was just as warm and humid as it is now. There was no ice at the poles, and single-celled prokaryotes floating in waterways produced oxygen, which would later ensure the development of all life on Earth. Clearly, these two scenarios contradict each other. Scientists claim the planet remained warm during this time, but how could it manage to do so? The heat might have come from the Earth's crust, which was still cooling after the planet was formed and gravitationally packed. Most likely, the heat was retained after an impact with a protoplanet, probably the size of Mars, which led to the formation of the Moon. Early tides between Earth and the Moon were extremely strong, and as a result, the Moon became tidally locked within just 100 million years of its formation. The tidal heating may have raised Earth's surface temperature and triggered worldwide volcanic eruptions. Emissions of gases into the atmosphere from such events created a potent greenhouse effect. Likely, carbon dioxide and methane were the main contributors to this expansion. There were nearly no clouds in the Archean sky since clouds usually form when sunlight evaporates water, but there was very little sunlight and hence very few clouds. However, the intriguing clouds reflected a minimum of the sun's radiation back into space. Vast amounts of methane could have filled the sky, creating a thin photochemical cloudiness that tinted the clouds pink. This stunning display lasted until about the end of the Archean age. Then, as oxygen levels in the atmosphere increased, methane oxidized, and the clouds took on their characteristic snow-white appearance. You've heard of many peculiar things happening in the universe, but odd things are also happening around our Milky Way. One of the greatest oddities in physics is the black hole information paradox, a puzzle arising from the combination of quantum mechanics and general relativity. Measurements show that physical information could permanently vanish into a black hole, allowing physical states to degrade into something indistinguishable. However, this is controversial because quantum mechanics asserts that information can never be destroyed. Let's imagine you burn two different letters that were written down. Reconstructing them from the ashes would be nearly impossible, but not entirely. The slight differences in smoke temperature and the amount of ash would still carry information about the two original letters. The problem with black holes is that they suck things in and then over time, emit what they've swallowed back out as Hawking radiation. Unfortunately, unlike the smoke temperature and ash from burning a letter, Hawking radiation contains no information about what the black hole has consumed. All Hawking radiation is the same, meaning that black holes destroy information about the universe. So, do evaporating black holes truly destroy information, or does information escape? A new generation of physicists claims that information indeed escapes a black hole through its radiation, and they have identified an invisible surface within a black hole's event horizon called the quantum extremal surface. This surface appears to encode the amount of information emitted from the black hole, accumulating over the black hole's lifetime. As expected, if information escapes, clearly something can escape from a black hole. The conundrum of missing dwarf galaxies, according to the standard model of cosmology, suggests that large galaxies should have hundreds or even thousands of dwarf satellites orbiting them. Yet only about 30 have been found around the Milky Way, roughly 1% of the expected number. So, where are the missing dwarf galaxies? One idea is that, over the course of evolution, larger galaxies might have captured these smaller systems through gravity. Alternatively, it could have been the result of some catastrophic event in the vastness of space, but perhaps we simply haven't been able to trace them yet. By and large, they're incredibly small and faint, some contain only a few thousand stars. Meanwhile, the Milky Way holds 100 to 400 billion stars, and with the brightness of its stars, it dominates the faint impressions of these tiny galaxies. The catch-22 of the missing Milky Way ultra-faint dwarf galaxies doesn't end there. These small galaxies challenge the entire Newtonian model of gravity. The issue is that their rotation is odd. In the cosmological model, galaxies are supposed to form as individual objects before being captured by larger galaxies, and because they would be coming from various directions, they couldn't be arranged in a circular pattern. However, the 11 brightest dwarf galaxies are arranged exactly that way, and all galaxies orbit the Milky Way in the same direction. This is somewhat similar to how the planets in our solar system orbit the Sun. According to scientists, this arrangement must be explained by assuming gravity is stronger than expected according to Newton, and that's where the conundrum arises. Researchers suggest that dark matter clusters in these tiny galaxies aren't large enough to attract gas and form stars, making them invisible to us. Dull matter ties space objects together by its gravity, and there must be a ton of it. Cosmologists at Cambridge College have learned about 7,000 systems and tracked down there's multiple times more dim matter there than common matter. Anyway, in May 2022, cosmologists at the College of Barcelona in Spain reported the conceivable disclosure of 11 universes absent any and all dim matter inside dim matter systems. Stars should move a lot quicker than Newton's hypothesis of gravity predicts, so in the event the information suggested by the Spanish stargazers is confirmed, Newton's hypothesis should be adjusted. This will not be the initial time the key standards of material science must be changed, and this all generally prompts major changes in the manner we see the universe. We've made the Webb, arrived on the Moon, found the Higgs boson, and our shuttle have entered interstellar space. It seems that in the past 100 years we've achieved more than we might ever consider, and it's hard to imagine that we could go any further. But imagine a scenario where that is only the tip of an iceberg. Imagine a scenario where all human advancement is only our aggregate deception over time. The Kardashev scale of a civilization's innovative headway has extended and limited. One of the ideas is that there are 4 degrees of civilizations in the Kardashev scale. Type 1 civilization, or a planetary civilization, would be capable of reaping all the energy resources available on its planet. Type 2 civilization or stellar progress would go further, having the ability to harness the energy of a whole star, essentially allowing it to control an entire planetary system. A Type 3 civilization or cosmic progress could use the energy resources of a whole galaxy, move planets, and feed black holes with stars. But even that is far from what a Type 4 civilization would be capable of, which would involve creating a universe itself. According to this scale, we haven't reached Type 1 civilization status, but we're not a Type 0 civilization anymore. So, where does this leave us? Type 0 on this scale means a particular measure of energy consumed by a civilization, which is about 1 megawatt of power. As of now, our average annual energy consumption is around 17.7 terawatts, and simply a single terawatt would be enough to power 10 billion 100-watt lights simultaneously. Humans have a score of around 0.73 on the Kardashev scale, but how fast might we reach the achievement of Type 1 civilization? One renowned theoretical physicist has estimated that, assuming we increase energy usage by 3% annually, it would require 100 to 200 years to reach Type 1. Currently, around 1 billionth of our star's energy reaches Earth, and we only use 1 millionth of that. Once we achieve this status, we'd be able to use all the sunlight, wind, and tides available to us. Weather patterns would be controlled by us, and we'd change the direction of earthquakes and volcanoes and create floating cities on the water. This sounds like we'd have superpowers, but that isn't anything compared to what civilizations of Type 2 are capable of. A Type 2 civilization, also called a stellar civilization, would go much further than harnessing energy from its home planet. At this level, advanced beings would control their whole parent star's energy output, and there are multiple ways to do it. One idea is to use a superstructure called a Dyson sphere. Its simplified version, a Dyson ring, would consist of a lot of solar power collectors surrounding a star, for instance, around 160 million kilometers. As this civilization continues advancing its technologies, it would add more rings around the star, each with its own orbit. Eventually, this superstructure, the size of our planet's orbit around the Sun, would look like some sort of shell encompassing a star, blocking most of its light, but also gathering most of its energy for us. The creation of such a technology would be nearly equivalent to the development of power star lifting. It's another method to take some energy from a star. But how exactly does it work? A highly advanced civilization, halfway to Type 3, might know how to siphon material from a star and place it into a rotating black hole's ergosphere. The ergosphere is a region around a black hole just outside its event horizon, and many fascinating phenomena occur there. By sending material into this region around a black hole, you could get energy back out at much higher speeds. This is known as the Penrose process, and according to this, about 29% of the energy in a black hole could be extracted. But there's a downside to this method. A black hole will begin spinning slower and eventually stop. However, this also opens up another possibility: harnessing radiation from evaporating black holes, which is far beyond our capabilities but would barely be advanced science for a Type 3 civilization. This cosmic-level civilization would basically use the same technology as a previous one, but on a much larger scale. We're talking cosmic scales. Whole galaxies would be filled with Dyson spheres surrounding billions of stars. New planetary systems would be artificially created, their supplies of energy would be limitless, and they would essentially become immortal. The only thing that would threaten their existence would be a sudden natural disaster, such as the massive explosion of a supernova. For humans, it might take 100,000 years to become as advanced, and it might really take 1,000,000 years to become a Type 3 civilization if we ever survive long enough. But do such civilizations exist? And if so, such a serious technological advance would be easily detectable in space. According to NASA, we found around 4,000 planets outside our solar system in the past 20 years, and in the Milky Way alone, there should be trillions of stars joined by planets. So, why haven't we found any signs yet? This is known as the Fermi paradox, and it says that our universe is too old and too vast for there not to be a single other life besides the one we have on Earth. Yet, throughout many years, we haven't found any such thing. We might not have looked enough. The ongoing search for extraterrestrial intelligence is limited to getting some frequencies of radio and television emissions. The problem is, such signals must be made by a Type 0 civilization, and because they also block static charges in space, a good portion of that signal is lost. A much more effective way is to break signals into all frequencies to preserve the majority of that signal. Unfortunately, a theoretical Type 0 civilization using only a single frequency wouldn't be able to fully read that message, hearing instead the noise. So, even if the Milky Way is filled with other signals from Type 2 or Type 3 civilizations, human Type 0 radio telescopes can't hear them properly. Another scientist at the National Astronomical Observatory of China came up with a new theory of where those civilizations could be hiding. A professor and her team checked a large portion of the sky and identified 21 systems. They were looking for surprising radio transmissions to detect alien waste, and the two strange worlds they found had enhanced infrared emissions that couldn't be explained by normal phenomena. Cosmologists believe this could point to a lot of Dyson spheres or entire galaxies captured by an advanced civilization. But to prove this idea, they need to know for sure what's causing these infrared emissions. There's also another theory to explain the Fermi paradox. Maybe these civilizations have chosen to stay hidden. Our universe is enormous, and just because we haven't succeeded in finding anyone doesn't mean they're not there. When searching for signs of technologically advanced civilizations, astronomers often base their observations on various kinds of infrared emissions and waste. But what if a hyper-intelligent civilization has not only come up with incredible technologies but has also figured out how to hide its presence? If that's the case, all this time we've been looking for something we shouldn't and have ignored what deserves our utmost attention. If we continuously fail at finding any signs of extraterrestrial civilizations, we might try focusing on where things are going wrong instead. The most likely scenario is that if a Type 3 civilization existed far out in the distance, it would gather all the energy available in the universe and exhaust its entire power supply, leaving nothing behind. And there are such empty regions in space, the great voids, which were once believed to be marks of intelligent life. But this theory was disproven, and although researchers haven't lost hope, most of their studies eventually reach a dead end. And if that's generally the case, there arises another question. What if we just came to be at the wrong time? According to one programmatic hypothesis, intelligent life might have been more abundant long ago than at any other moment. It might seem amazing, but if primitive life existed on Earth about 3.5 billion years ago, why couldn't intelligent life exist somewhere else in the universe around the same time? And should we even try to satisfy our natural curiosity, with the risk of possible extinction of humanity as a species? We all come from one ancestor, and we can't control our anger toward one another. So, should we imagine that a hyper-advanced civilization would care more about our lives than we do today? We're afraid of depleting our planet's resources. Type 2 civilizations would fear the death of their star, and Type 3 civilizations would be concerned about escaping the death of the universe. But if we take a look at a more extensive adaptation of the Kardashev scale for a Type 4 or even Type 5 civilization, even that wouldn't be something to stress over. These animals could hypothetically shape another universe, and as per one physicist, the energy expected to bring forth a child universe in a research facility would require around 1,000 trillion degrees, which is far beneath the limit of such a civilization's capabilities. In spite of the fact that Type 4 civilization is scarcely ever reachable, it would in a real sense mean becoming the makers of all that we might at any point notice, think, or imagine. Given how fast we advance, and that even today the formation of successful miniature laser-moved rockets is within our arm's reach, the facts could prove that we've already been visited before. The chances of seeing them are practically zero, but even now, we might be noticed by a substantially more advanced civilization that simply holds up until we gain sufficient headway to eventually reach out. Or perhaps they've already chosen to connect, but it will require countless years for them to show up here from another world at the other corner of the universe. But regardless of whether we find anyone, it doesn't necessarily mean something bad. Sure, we would feel forlorn and perhaps abandoned, but this would also imply that we get the opportunity to set the foundation for the future stages of human development. One day, those hyper-intelligent animals resembling us in appearance could consider us pioneers, aimlessly discovering this dim spot we were placed in as a child. Perhaps the entirety of our imagination makes us think they exist, and maybe they do. But it's not them, it's us. Future us. Godlike creatures. Applause. You might have heard the term Fermi's paradox before. In its least complex form, the term asks the question, if intelligent life is common in the universe, where is everyone? You may be thinking that the physicist Fermi wrote papers regarding the matter, and that his main purpose was based around finding extraterrestrials. But this couldn't be further from reality. Enrico Fermi was a physicist who made the world's first model atomic reactor. He never really expounded much on extraterrestrials. Fermi was talking with partners at a lunch in Los Alamos about an animation showing aliens rising from a flying saucer, carrying garbage bins taken from New York City. That's when Fermi asked, "Where is everyone?" Everybody recognized he was alluding to the fact that there was no solid proof of extraterrestrial visits to our large blue planet. The discussion then turned to the subject of interstellar travel, where Fermi concluded that interstellar flight could not be conceivable, probably wouldn't be worth the effort, or a mechanical human civilization doesn't last long enough to develop interstellar travel. Remember that Fermi was considering this in 1950, when rockets hadn't yet reached Earth's orbit. The so-called Fermi paradox, which questions the existence of extraterrestrial civilizations, really distorts Fermi's perspectives. Fermi didn't question the possibility of alien civilizations, only their ability to have interstellar travel. So, what is the Fermi paradox? If Fermi didn't make it, who did? In 1975, an astronomer by the name of Michael Hart wrote an article in which he said, "They are not here, therefore they don't exist." Hart's claim was that if intelligent aliens existed, they would inevitably colonize the Milky Way. He believed that if they were anywhere, they would be here by now. Since they aren't, and we've seen no signs of aliens, it means that humans are the only intelligent life in our galaxy. And if that's the case, searching for intelligent life elsewhere is probably a waste of time and money. But then another famous physicist, Frank Tipler, appeared in 1980 and expounded on Hart's evaluation and posed the big question: where would a civilization get the resources needed to colonize 1 billion stars? He came up with an interesting idea where a civilization could build an artificially intelligent machine, similar to the current human level, that could replicate itself. If you sent one of these machines to a neighboring star and told it to build copies of itself using local materials in that system, then you could send those copies out to another adjoining star, until the galaxy would crawl with self-replicating machines. Tipler said that since we haven't seen any of these machines, we are the only intelligent civilization in the universe. Now, we truly have no clue how many advanced extraterrestrial civilizations may be out there that could pull off such an accomplishment. But a man by the name of Frank Drake came up with an equation that gives us a good guess of how many civilizations in our galaxy might have signals we could detect. And although civilizations could exist in the thousands, various answers for the Fermi paradox have been suggested over the years. One answer to the alleged Fermi paradox may be the most startling of all. It's known as the dark forest hypothesis, written by Chinese sci-fi author Liu Cixin, and it's potentially the most chilling hypothesis, as you'll soon find out. Imagine the universe as a vast dark forest, and us humans, along with other advanced civilizations out there, are the hunters. The hunter doesn't light a light to make himself visible, because while it may be harmless, it could bring the jaws of an eager lion or worse, get the attention of another competing hunter. Now, we don't have interstellar travel yet, but as far as interstellar communication, it's possible with advances in hardware that is already available. Lasers could easily send messages across the galaxy. Of course, there could be delays in the signal due to the speed of light, but we've done much more than just send a few radio transmissions. In fact, we've done almost everything but be quiet, from purposely sending messages and spacecraft out into space to unintentionally broadcasting radio and television signals that spill into space. The Voyager probes are already on their way out of the solar system, and if there is intelligent civilization out there, it could be detected. These two probes essentially carry all of humanity with them. That could be something to be thankful for, or it could be something terrible. That said, we've already lit the light in the dark forest. The next question is, who or what will detect our signal and come to investigate? This should make everyone anxious. Famous sci-fi author Arthur C. Clarke once said that two possibilities exist. Either we're alone in the universe or we're not. Both are equally frightening. We should realize that it's difficult to know the intentions of a newly encountered civilization. If one was ever found, it might be possible that some extraterrestrial civilization might have studied us, seen our destructive nature, and decided leaving us alone is better. We could end up wiping ourselves off the planet, let alone worrying if someone will do this to us. We could end up being lucky, and a more advanced civilization would step in to help us reach the stars and become an interplanetary species by sharing their technology with us. There may be peace on Earth after the realization of not being alone in the universe. But we need to be realistic and wonder, why would another civilization do this? Another advanced civilization out there might be terrified of how we could treat them if they were discovered. On the other hand, it might be in human civilization's best interest to shoot first and ask questions later to avoid being destroyed or wiped out by another more advanced civilization, as we've seen in several sci-fi films like War of the Worlds. No one knows who would destroy whom in the first meeting. It's almost a given that if a civilization has discovered interstellar travel, their weapons technology is likely far more advanced than anything we have here on Earth. That is what the dark forest hypothesis suggests. It's possible all other civilizations out there in the universe have decided to remain silent out of fear of being destroyed. But the most terrifying thing about this remains, and there's no way around it. We've just been too loud. It may be the case that there are all sorts of extraterrestrial civilizations out there who know we exist, but the reason we know so little about them is because they haven't been sending signals like we have from Earth. A smart alien civilization out there that has found Earth may not see us as a threat, because we haven't reached a technological level for interstellar space travel. But they could be waiting for that moment. They could be waiting to see if we will continue to be a silent race, or if our planet will become a threat to all life. In any case, it would be very difficult for another advanced civilization to stop accidentally broadcasting radio transmissions into space like we do, unless they're more advanced and use another form of communication that we can't detect here. And that brings us to another possibility. Why we don't know or hear anything from space. Maybe there truly isn't anyone out there. That's hard to believe because there are upwards of 40 billion Earth-sized planets in habitable zones. But the mystery continues. In spite of the way that the universe might be abounding with habitable planets, there's no assurance they'll remain that way long enough for life to develop. As indicated by a new study from Australian National University, wet, rocky planets like Earth are quite unstable when they're first formed. If any sort of extraterrestrial life desires to advance and flourish with a Terran planet, there's an extremely limited window of only 200 or 300 million years to get everything going. Think about our own planet and what it's experienced. From a wad of magma being pulverized by space rocks, to a freezing ball of ice and then back again. The opportunities for life to prevail on an initially wet, rocky planet in the habitable zone are very troublesome. It isn't so much that life may be rare or difficult to get started in the universe, but the habitable conditions aren't steady during the initial billion years. Of course, on account of our Earth, we are here. We know from our own discoveries that the universe is a dangerous place. Everything it takes is a cosmic explosion, a gamma-ray burst, a solar flare, or an immense space rock to wipe out life on a planet. We know some of those things have happened here on Earth. It may be hard to deal with the idea that we're the only intelligent life in the Milky Way, or maybe even the entire universe. Perhaps after all these billions of years, other human civilizations have come and gone, and maybe we're the last ones remaining in the universe. As for the Fermi paradox, there really isn't one. We can't say that extraterrestrials exist or not because nobody knows whether travel between star systems is possible. However, there was a part of excitement when the Central Intelligence Agency declassified a huge number of UFO records. In some of those 3 million documents, there was insufficient proof to identify objects detected on airplane instruments. Perhaps extraterrestrials are here now, and we just don't know about them. Whether or not we have or haven't been visited by extraterrestrial beings in our universe, UFO experts say that humankind is closer than ever to finding the presence of alien life. With all the telescopes we have looking through space, we are bound to find something. So, what do you think? Do you think we'll find proof of life out there in the near future, and should we continue to search for aliens? Astrophysicists are attempting to figure out what annihilates whole galaxies in the most extreme regions of the universe. Researchers at the International Centre for Radio Astronomy Research in Australia have studied more than 11,000 galaxies and concluded that their gas and dust are being stripped away. Without this building material, galaxies stop forming new stars and the old ones eventually disappear. So, what's causing galaxies to be consumed by some mysterious cosmic force, and what huge inconsistencies still resist explanation? One thought is that this is caused by the expanding expansion of our universe. Speed may simply be as dangerous in space as it is on the road. When galaxies start moving too fast in their clusters, tempests can arise within them, capable of quickly pushing gas out of galaxies. But there are other potential ideas. Black holes are believed to be located at the center of most galaxies, and due to the strong radiation of matter inside these black holes, powerful particle streams burst out of them. These enormous jets can blow everything out of a galaxy. Another possibility is that galaxies are digging their own graves. They start consuming stars much faster than their neighbors and lack the time to recover their gas reserves. This leads to their slow elimination, which researchers call strangulation. Whatever the reason for this mass destruction is, researchers struggle to understand the existence of certain galaxies. These are extremely hot Jupiters, huge gas planets like our Jupiter, that orbit extremely close to their stars. Researchers don't understand how it's possible for their existence to be in front of the rest of the competition, but there are three theories. The magnetic field of a parent star could be a protective barrier for a gas giant, or the red line for a planet is its dust ring. A gap is formed between the inner edge of such a ring and a star, killing the attraction of that star. On the other hand, a planet's approach to a star stops when the extended ring of a hot Jupiter transforms into a circular orbit. While researchers search for evidence to back up their hypotheses, giant planets continue to surprise specialists. Take WASP 121b in the Puppis constellation, for instance. Lying 850 light-years away from Earth, the planet is 1.74 times the radius of Jupiter and 1.157 times its mass. The giant orbits so close to its star that it completes one orbit in only 30 hours, more than 3 times faster than Mercury orbits the Sun. Particles of liquid iron, magnesium, chromium, vanadium, aluminum, and titanium form clouds on the cooler half of the planet. Aluminum combines with oxygen, and along with other combinations of chromium, iron, titanium, or vanadium, drops form either rubies or sapphires which could fall like rain on the planet. However, no alien life would be able to utilize these gems because of the proximity to its star. WASP 121b is about 2,700 degrees Celsius, making the presence of protein life there impossible. Although most objects in the universe meet their end in a peaceful elimination, some of them cease to exist in a more dramatic way. Back in 1967, the Manor satellite intended to monitor secret Soviet nuclear tests, detected a blinding flash of gamma rays outside the solar system. Gamma rays are an extremely powerful form of electromagnetic radiation, and astronomers observe about 1 gamma ray burst per day in distant galaxies. These flashes in space occur due to some of the most powerful and brightest explosions in the universe. Their duration can range from 10 milliseconds to several hours. When something like this happens, sometimes the amount of energy released is about as much as our Sun emits in 10 billion years. Astronomers have been able to detect stars that turn everything around them to dust during such events. Prolonged gamma-ray bursts occur during hypernovae or the death of a star with more than 30 solar masses. Occasionally, an explosion can be 100 times more powerful than a regular supernova. These dead stars leave behind giant, rotating black holes. Brief gamma-ray bursts are also believed to be caused by neutron stars. Due to a wave in space, a neutron star can collide with another neutron star or be consumed by a black hole. The nature of such events is still not fully understood. Recent observations have shown that after gamma-ray bursts occur, all photons travel in the same direction, and then suddenly at some point in space they mysteriously change their path. It's also strange that gamma-ray bursts have energy concentrated in a narrow beam, so our satellites don't detect many of them. Astronomers estimate that there might be around 500 gamma-ray bursts occurring every year. Researchers believe that the LIGO Observatory Laser Interferometer Gravitational Wave Observatory, which is extremely sensitive to gravitational waves, will be able to record many more gamma-ray bursts. We can only hope they don't find gamma-ray bursts anywhere near the Milky Way. One was previously detected near our galaxy about 2.7 billion years ago, and it caused an ice age on Earth which ended with the Permian extinction, one of the 5 largest in Earth's history. Another burst near Earth would likely destroy the ozone layer of our planet. If this happens, all life would cease to exist due to the harmful ultraviolet radiation. However, since there are no neutron stars in the vicinity of the Milky Way or contenders for supernovae or hypernovae, researchers are confident that the likelihood of such an event is near zero. There will certainly be other risks found to our solar system and to our planet in the future, but for now it doesn't look like we have anything to worry about, except for the occasional asteroid that flies by our planet, sometimes unexpectedly. Most galaxies are structured with fibers of gas and dust between stars, a kind of cosmic skeleton that seems to hold everything together. A few moments after the Big Bang, dark matter and dark energy spread throughout space, and a sort of web was formed. Dark matter is believed to be responsible for the large-scale structure of the universe as we know it. But wait, what is this stuff we're referring to? Dark matter is believed to be a non-luminous material that makes up around 27% of the universe, and could take the form of various types of particles, including weakly interacting particles or randomly moving high-energy particles. Dark energy, on the other hand, is an unknown form of energy believed to make up approximately 68% of the universe. Scientists found evidence of dark energy by measuring cosmic explosions, which showed that the universe doesn't expand at a consistent rate, but is actually accelerating. In simpler terms, dark matter is like glue or cement that appears to be holding the universe and everything in it together, and dark energy is the force that is pulling everything apart. The universe is expanding in every direction and speeding up its development. So, what's so unique about this? Investigate this picture of the galaxy NGC 1052 DF2 from the constellation Cetus, which is found 62 million light-years from Earth. Right away, there's not a big deal about the picture, aside from the fact that this galaxy has many fewer stars than the Milky Way. However, this isn't what truly got researchers' attention. The galaxy, along with its neighbor, galaxy NGC 1052 DF4, is believed to be missing all dark matter. The largest map of the universe's dark matter was created by cosmologists at the observatory in Chile and shows this peculiarity. So, why is there no dark matter in the galaxies from the constellation Cetus? Moreover, how do these two galaxies manage to survive without self-destructing? One idea is that larger, neighboring galaxies have taken gas from galaxies DF2 and DF4, and now they're destroying their smaller neighbors. In the latest study, cosmologists have suggested that around 1 billion years ago, two diminutive dwarf galaxies crashed into one another. The vast disaster resulted in a dispersion of gas, which formed a large number of new dwarf galaxies. Eventually, the two infant galaxies didn't acquire dark matter, so they now need to survive without a skeleton. But this isn't all that has cosmologists confused. More than 400 exoplanets found by researchers shouldn't have survived either. We generally consider gravity to be a force between objects with mass. It's easy to perceive how this force works by stepping on a scale to see how much you weigh. The number on the scale represents the Earth's gravity on your mass, or your weight on planet Earth. With regard to gravity in the universe, we can imagine the Sun's gravity keeping the planets in their orbits, and we're all familiar with the strong gravitational pull near a black hole. The so-called force of gravity is straightforward, and gravity could seem like a simple thing. After all, we've known it for centuries. However, the situation has changed in the modern age. As we now know, gravity as a force is just a small part of a more complicated phenomenon, thanks to the general theory of relativity. But before we get into that, it's time for a little Physics 101. Everyone is familiar with Newton, who was a real giant of physics in his time. The story about the apple falling on his head. Well, that didn't really happen. In truth, Newton saw an apple fall from a tree and was in a pensive mood. At that moment he wondered why the apple fell straight towards the ground and not sideways or toward another path. He proposed that a force of gravity between two bodies pulled them towards one another, with an extent directly proportional to their mass, and also inversely proportional to the square of the distance between them. The path that the bodies take would be the shortest to minimize energy use, hence a straight line. In short, Newton believed an apple falls because a gravitational force accelerates it towards the ground. Newton probably thought there was something missing from his theory, but since he wasn't totally happy with it, he didn't realize he was partially right. Still, his theory of gravity was accepted as gospel, that the magical pull was a fundamental property of mass, the theory which endured and clouded the truth for the next 400 years. That was until Albert Einstein, another monumental genius, arrived in 1905 and introduced his general theory of relativity. While working as a Swiss patent clerk, his challenge to Isaac Newton's theory was initially dismissed or disregarded entirely because his ideas seemed too radical to be possible. The key to understanding the theory of general relativity is that everything in a gravitational field falls at the same rate. However, it wasn't Einstein who figured this out. It was Galileo who first concluded that all objects, when released in the absence of an environment, fall at the same rate regardless of their mass. A famous experiment by Apollo 15 astronaut David Scott was conducted on the Moon to test this hypothesis. Simultaneously, moonwalker astronaut Scott dropped a hammer and a feather, and both of them floated to the ground, impacting the surface at the same time. Exactly the same thing would happen for any object, no matter what its mass or physical composition. This is known as the equivalence principle. So, why do the two objects fall together and land simultaneously? This is because they aren't falling, they're stopping, and there is no force acting on them. With Einstein's theory, gravity isn't a force between two objects with mass. Instead, gravity is the warping of space and time in the presence of objects with mass. Without any force acting on the objects, they will move in a straight line. Einstein believed that smaller objects are not pulled on by larger objects, but rather the objects are being moved by the space above them. There is no such thing as a gravitational force according to Einstein's theory. Matter bends not just the fabric of space but time too. This is called spacetime, and any object in space bends this spacetime continuum. Spacetime consists of the three dimensions of space, length, width, and height, combined with the fourth dimension, time. The more massive the object, the more it bends the space around it. Einstein believed that apples fall from trees and planets orbit stars because the objects are moving along curves in the spacetime continuum. These curves are gravity. A good guide to understanding how this works is to imagine the Earth on a grid of spacetime. You can see that the mass of the Earth bends spacetime and creates a sort of gravity well. Any object around this mass, such as you, me, and even the Moon, is pulled down and towards this gravity well. The Moon also bends spacetime with its mass, but the gravitational field between the Earth and the Moon isn't strong enough to pull the Moon towards us. Instead, it's like an apple falling from a tree. The Sun also has a huge gravity well that keeps everything in our solar system from flying off into space. We can also understand how gravity wells around planets in our solar system work by how we've launched spacecraft to get satellites moving in different directions. Engineers use bent spacetime or gravity around different planets in our solar system to perform gravity-assist slingshots, sending the spacecraft in another direction with greater speed. The closer an object is to the planet, and thus its gravity well, the faster it will begin to move. The bottom line is that objects in the universe are drawn to each other because spacetime is bent and warped. The closer they are to the target mass, the faster they will accelerate. But what about this supposed gravitational field we were talking about earlier? It's not a force. A gravitational field is actually the field of force that exists in space around every object with mass. The Moon has a smaller gravitational field than the Earth due to its mass, but the Earth has a much stronger gravitational field because of its greater mass. However, in space, a gravitational field exists everywhere. With everything floating in space above our heads, it might be easy to believe there is no gravitational field at work in orbit around our big blue planet. However, even the International Space Station feels the gravity of Earth. The amazing thing is that the powerful gravity in orbit around the world is nearly equivalent to the one on the surface of the planet. In fact, it's about 90% as strong in orbit as on the surface of the Earth. So, if you weighed 100 kilograms on Earth and had a space ladder that reached all the way to the space station, you'd weigh around 90 kilograms up there. But wait a minute. If there's gravity in space around the world, why do astronauts appear to be floating in zero gravity? The reason astronauts appear as though they're floating in space is that everything, including the International Space Station, is falling together at the same time. In the vacuum of space, this condition in which it seems people and objects are weightless is called microgravity. If everything falls in the same way, regardless of its mass, then a free-floating astronaut far from any gravitational source, and a falling astronaut in the gravitational field of a large body, would each have the same experience. In fact, the space station, satellites, and everything else up there are constantly falling toward the Earth. The worldwide space station is falling. It's also moving exceptionally fast at around 28,000 kilometers per hour from the pull of the Earth's gravitational force. There are ways to prove Einstein is correct about objects with mass distorting the fabric of the universe called space-time. The gravitational acceleration at the Earth's surface is 9.81 meters per second. The reason gravity pulls you and other objects towards the ground has nothing to do with the center of the planet. All objects with mass twist and bend spacetime, and that arch of space is gravity itself. So, if you were to somehow make a journey to the center of the planet, there would be no gravity. You would be away from the curve of spacetime at the center of an object with mass, and thus floating around the planet's center weightless. However, as you began to move back to the surface, you'd start to feel the shape of spacetime from the mass of the Earth, and the effect of that bend, gravity, would begin to get stronger. Of course, we'll need a test to travel to the center of the Earth to nail that one down, but there is another way to prove that gravity bends spacetime. One of these methods is called gravitational lensing. This happens when a huge celestial body causes a sufficiently large bend in spacetime that the light around the object appears noticeably twisted, as though you are looking through a camera lens. This gravitational lensing happens when a massive object like a galaxy bends the space around it into rings of light. Strangely enough, this has helped us discover other galaxies and objects in space that we wouldn't otherwise see without the gravitational lensing effect. Einstein's cross is a famous example, showing a gravitationally lensed quasar that sits directly behind the center of a galaxy. For pictures of the quasar appear in the foreground because of the strong gravitational lensing of the galaxy at the center. It might seem like Einstein has this whole thing figured out, and there's a lot of evidence supporting general relativity, but here's the big issue. In its current form, it's incompatible with quantum mechanics. Quantum gravity is theoretical physics that seeks to describe gravity according to quantum mechanics. However, there is no theory of quantum gravity that is widely accepted or confirmed by experience. That's not all, though. Scientists understand that at some point within a black hole, Einstein's theory breaks down and stops working. Researchers use 3 giant telescopes in Hawaii to watch a blue star called SO2 make its closest approach to the black hole Sagittarius A** in the Milky Way galaxy. In its 16-year orbit, if Einstein's theory were correct, the black hole would twist spacetime and expand the frequency of the light from the star. The waves of light would stretch out as the gravitational pull of the black hole would drain their energy, causing the light from the star to shift from blue to red. And just as Einstein predicted, the star began to shine red. Had it been another color, it would have indicated something completely different about gravity. Currently, researchers are searching for a shape of spacetime that is so extreme, the theory of general relativity would fail. They believe that within the next 10 years, the theory of general relativity will be pushed to its limits, and a new genius will come along and show us where Einstein was wrong. Let's hope we don't have to wait another 300 years. In 1994, it seemed like the Hubble telescope caught an object depicting a beautiful city with snow-white towers floating in space. People called it Paradise or Heavenly City. Followers of alien civilizations were excited, and even speculated that the city was the center of our universe. However, after a careful examination, astronomers announced the picture was fake. Researchers later explained that the Hubble image caught galaxy NGC 3079. Part of the image was cut out, photoshopped, and a divine paradise was created to trick the world. And despite there being nothing mysterious in the picture, it has sparked widespread interest in the structure of our universe. So, does the universe have a center, and how would we know if it exists? Since ancient times, the sky, dotted with the lights of stars, has intrigued people, and they were curious as to whether there was a center to this vast cosmic expanse. Our ancestors related it to something natural and recognizable like flowers. Egyptians considered the sky as a lotus, and its center as the focal point of the universe where gods resided. Later, the ancient Greek philosopher Aristotle concluded that the planets and even the sun revolved around Earth. In the 16th century, Nicholas Copernicus was convinced that the Earth itself revolved around the sun, which was thought to be the center of the universe. In the 20th century, improved telescopes revealed how vast the universe is. At the start of the century, American astronomer Harlow Shapley made a map of the Milky Way. According to this, the Sun is just one of 100 billion stars in the far corner of our galaxy's spiral arm. Then, in 1929, American astronomer Edwin Hubble demonstrated that there are billions of galaxies in the universe, and our own is not special. Today, our planet's cosmic address is extremely long. The Solar System, Orion Arm, Milky Way Galaxy, Local Group, Virgo Cluster, Laniakea Supercluster, the universe. This by itself shows how complex and vast the structure of the universe is. Everything in the universe spins, from small asteroids to entire galaxies, but does the universe also rotate? If it's possible to figure this out, we can pinpoint its center, a fixed point on a rotating object. The center of Earth's rotation is the axis connecting the north and south poles. For a basketball player spinning a ball on his finger, the center of rotation is the point of contact between his finger and the ball. But it seems that the universe has no such point. All of our observations show that unlike stars, planets, and galaxies, the universe does not rotate. This would make it difficult to find its center in the conventional sense. But perhaps we can find it through mass. If an object has an end, it must have a start, and the center would be a point with an equal distribution of mass. However, according to the standard model of cosmology, the universe is isotropic. It's the same everywhere. Of course, the mass of galaxies varies in some of its areas, but on average it's the same across vast regions of the universe, millions of kilometers in size. The universe is like a sponge, an enormous one. It doesn't matter whether you're looking at this super sponge from Earth or from the most distant exoplanet ever discovered. The picture won't change much. The problem with finding the center of mass in a homogeneous space is that it's impossible. However, another aspect of the cosmological model, the expansion of the universe, might provide some insight. In 1929, Edwin Hubble estimated the speed of galaxies at various distances from our planet. Hubble noted that galaxies are flying away from Earth and speeding up. Because of this, we can assume they all started moving from the same spot. In everyday life, finding the place of origin of an object is simple. Screw a rubber sheet to the ground, and then ask your friends to pull it from all sides. You'll notice that the place where the sheet is attached is the center of its expansion. The same applies to the universe, right? Since cosmologists can see the movement of galaxies from Earth, our planet should be a kind of center too. Well, the way the universe is expanding works differently. Researchers have found that galaxies fly away when observed from any point in space, not just from Earth. The farther away from the observer, the faster galaxies recede. So, how does this work? According to Edwin Hubble's calculation called the Hubble constant, galaxies move away from one another at a speed of 70.4 kilometers per second per megaparsec, 3.26 million light-years. At 1 billion light-years away, the universe's expansion is pushing galaxies away at 22,000 kilometers per second, about 7 times the speed of light. But at 100 million light-years away, the speed is just 2,200 kilometers per second. So, when looking at galaxies from different parts of the universe, speculative movements would cause galaxies to move away faster or slower depending on where they are. Because of this, we can't pinpoint the center of the universe in this way. However, couldn't we measure it from the point of the Big Bang? We believe the universe was born about 14 billion years ago in the Big Bang, a massive cosmological explosion or expansion. We know that after any explosion, material expands from a particular point. It's sometimes possible to compute such a point, even with the naked eye. For instance, if you take a picture of fireworks and look at the direction of light flying overhead, it's easy to figure out where the fireworks exploded from. Does this mean we can apply this method to the Big Bang? Cosmologists believe we can't, and not because of the immense size of the event, but also because it happened when reality didn't exist. The Big Bang happened everywhere in the universe at the same time. Really, at that time, matter began to spread randomly. All through space, we know this on account of artifact radiation that arose after the big explosion. This is called enormous microwave radiation, which pervades space this way and that. Its general temperature is 2.7 Kelvin, yet in certain districts it tends to be colder in vast voids. The temperature of artifact radiation is a small part of a degree lower, yet no deviations from the typical temperature have been tracked down in larger areas of space. And assuming the big detonation had a focal point, it would have been a lot more smoking nearer to the focal point than somewhere else. Researchers look at the universe growing after the big explosion with a two-layered ball with focuses drawn on the surface to represent worlds. If we blow up the ball from within, it'll fill every which way similarly, and it will not have a particular community. The dots on it will turn out to be equally far off from one another. But the problem with this comparison is the universe should have an end. However, imagine a scenario where the universe is boundless. Researchers are finding more and more proof for this thought, and if so, we'll never be able to decide the true size of the universe. What's more, because of its middle speeding up increasingly fast comparative with the observer, eventually the extension should surpass the speed of light. And when this happens, we would end up surrounded by an event horizon. We wouldn't have the option to look past. But what might be said about the electric charge of the universe? Would it help us find a focus? Modern science tells us that the dispersion of the charge of the universe is, on average, homogeneous. There are equal quantities of items with negative and positive charges in immense areas of space, and thus the total electric charge of the universe is zero. So, we won't have the option to identify any unique point in space either. Up until this point, everything demonstrates the universe has no middle. And obviously it doesn't rotate, despite how a worldwide group of astronomers claims they could possibly pinpoint a focal point of our universe with the assistance of the alleged dim stream. Researchers made this speculation after studying cosmic groups from data gathered by the Wilkinson microwave anisotropy test. They saw that around 1,400 systems between the Diels and Centaurus groups of stars act strangely, not at all like others that move rather randomly. These astronomical objects move in the same direction. According to astrophysicists, cosmic system groups are gravitationally drawn in by something with supermass. This force drives the dim move through the entire discernible piece of the universe and even beyond its boundaries, and it does so with a crazy speed, at the very least 600 kilometers per second. Cosmologists propose that this stream is progressively pulling in more and more cosmic bunches, and their place of fascination could be the center of the universe. Researchers believe that this could be a black hole, and if this is true, it's so colossal it has no analogues in the known universe. Maybe the black hole is preparing for another big detonation. For this to happen, it would have to pull in and pack all the matter and energy of the universe into a unified peculiarity point. An interesting thought is that through the center of this black hole, our universe could drift directly into some parallel world. When we rest, we can barely distinguish reality from a dream. So, how do we know what's real and what's not? To researchers, something is real if it's not entirely set in stone before being measured. An apple can be green, even when nobody is taking a gander at it. However, the quantum world seems to observe different rules, and 3 researchers have recently won a Nobel Prize demonstrating our universe isn't locally real. But if our reality isn't real, what is this place we live in? Imagine there are 2 people, Anna and Luke, both situated on opposite sides of our local planetary group. 2 coins are sent from the center of the planetary group, each designated towards one spectator. While the coins are traveling through space, they're turning. According to quantum mechanics, it's difficult to predict which side the coins will land on. The outcomes are random. But when Anna measures heads, she immediately knows Luke's coin should have landed on tails. The chances of accurately predicting this even multiple times in a row is 1 out of 10 to the 60th, which is more than all the molecules in the planetary group. Despite the fact that Anna and Luke are separated by billions of kilometers, quantum mechanics says Anna can continue to predict Luke's outcomes based on what she got, like the coins had a sort of clairvoyant connection. This concept explores what's known as the Einstein-Podolsky-Rosen conundrum. It seems impossible, but this is the way the universe works. How could something travel faster than light? What is the pixel of our world, and how does the universe change from predictable to random? Before quantum mechanics, researchers believed that the world was deterministic. They thought that if they knew specific properties about an actual system, they could determine everything about the system, both past and future. But then, physicists discovered a peculiarity called quantum entanglement, which describes a state where 2 particles remain connected, no matter how far apart they are. This may not sound too exciting, but imagine this works even if the entangled pair is on opposite sides of the universe. This seems odd, even in the realm of quantum mechanics. We generally accept that nothing can travel faster than light, meaning there's a limit to how fast any signal can travel. But if you make entangled pairs of particles and send them in opposite directions, increasing the distance between them, and then measure the quantum state of one particle, the quantum state of the other particle will suddenly be resolved. You can imagine it as two boxes, each containing either a white or a black stone. So, whenever and wherever someone opens one of the boxes, they immediately know the stone in the other box. This has been shown across distances of many kilometers over time frames as short as 100 nanoseconds. 1 nanosecond is equivalent to 1/1000th of a second. So, if the two entangled particles somehow exchange information, they do it at least thousands of times faster than light. But that's not all. Just as we stand on scales to measure our weight, researchers measure particles to find their properties. But what if those properties only became determined the moment you measure them? This would mean our universe couldn't be both local and real. At least one, if not both, of these premises would be incorrect. Defining reality is a tricky thing to do. We don't see tiny particles, yet they exist. We can't touch the air, but it's there. So, what is truly real in physics? Real means that objects always have definite properties, whether or not we are measuring them or not. In other words, a falling tree in a forest makes a sound, even if there's no one there to hear it. Local means that objects must be affected by their surroundings, and that this effect can't travel faster than light. It's crucial that our reality is real, because as Isaac Newton believed, if you know the positions and speeds of all elements of our reality, and you identify the forces that impact them, physics can predict what the world would be like at any point in the future. But the quantum world often has inherent uncertainty. In short, it's not always predictable or even clear. Consider a simple experiment. Fill a container with a few radioactive particles and wait. It can generally be predicted how many particles will decay, and how many will remain. Anyway, you can never be aware for sure which molecules will and will not make it, or fire various particles through a barely separated double cut. You can predict what obstruction pattern will show up on the screen behind the cut, but you will never know where each individual molecule will land, regardless of whether they are being fired one by one. A few aspects of quantum physics seem, by all appearances, to be totally arbitrary. But are they truly random? Imagine a scenario where we simply need data. Albert Einstein believed that entanglement wasn't abusing local realism, but rather that quantum physics was incomplete. He felt that the factors connecting these entangled particles would eventually be found. The three researchers, John Clauser, Alain Aspect, and Anton Zeilinger, shared a Nobel Prize for demonstrating that these secret factors don't exist. The researchers concluded that an entangled molecule has no properties until someone measures it, and thus these properties can't be known or speculated in any way. So, if the universe isn't real, then what exactly is playing out? A group of physicists in Los Angeles has come up with a new theory of reality, and it depends on periodic patterns or crystals. Crystals can be of various shapes, but also of various dimensions. Even more so, a higher dimensional crystal can be projected to make a pattern in a lower dimension. The resulting pattern is known as a semicrystal. Physicists took an explicit 8D crystal, extended it to 4D, and at a specific point from it, they derived a 3D semicrystal, which they believe is the foundation of all reality. The central structure block of this 3D semicrystal is known as a tetrahedron, or a three-dimensional triangle with each of its sides of the same length. This length is the smallest speculated unit of length in existence, called the Planck length, which is 10 to the negative 35 times the size of a proton. If a particle were the size of the Planck length, it would be about the size of a proton. This is where it gets creepy. According to their hypothesis, just like digital displays consist of the smallest units of a digital image, pixels, a tetrahedron is a 3D pixel of our world. Every tetrahedron has only a couple of states in which it can exist, and the state of one tetrahedron defines the state of other tetrahedrons that occupy the entire space of the universe. But if a tetrahedron can only be in one specific state at a given moment, who or what directs the state it should be in? Physicists all over the globe believe that reality is made of information. But what is information? It is meaning communicated through symbols. But meaning is nothing else except for comparison, or the ability to see something in relation to something else. And if this is true, comparison and meaning require choice, in other words, consciousness. So, just like when we understand what the properties of an entangled molecule are when we measure them, meaning or information can exist when it's perceived or measured. If all of this is true, reality could be a result of consciousness. But there's another thought for our reality. The simulation hypothesis proposed by Oxford philosopher Nick Bostrom. Some researchers believe the chances we live in a simulated reality are 50-50. So, if we were somehow able to prove we're living in a simulation, how would we do it? We'd need to start with the idea that the hardware making the simulation doesn't have infinite processing power, because otherwise it wouldn't be possible to distinguish our existence from an artificially created one. Put differently, we wouldn't be able to notice any errors. Researchers are looking for ways to make a simulation reveal itself, with tests that would overload a hypothetical computer with limited processing resources. In the meantime, other researchers are finding other confirmations. All computing equipment leaves a trace of its presence inside the simulated reality it is running, so there should be a limit to the processing rate of activity per certain measure of time. And it happens that we have such a relic in our universe, the speed of light. It remains constant no matter what the observer, and it has a maximum limit that can't be explained by physics. So, we may not know what kind of computer is running our simulated reality or what properties it has, but there's one thing we can say for sure: if it performed one action per second, its memory compartment size for the variable space would be approximately 300,000 kilometers. Maybe we have this light speed limit because if not, we would be able to travel to another system before this computer could program it. But that's not the only sign we may be living inside a simulation. Movies or computer games often go into the perspective of characters to show things from their viewpoint. What we see on the screen and hear from the speakers is the coordinated experience that serves no purpose for the characters, it's there only for our benefit. So, if we accept the simulation hypothesis as our new reality, consciousness takes on a clear purpose. A coordinated emotional interface consists of 5 senses. No regular laws, philosophical or scientific, anticipate the development of consciousness, and there's no clear utility or evolutionary benefit it could provide. So, it seems its primary function is for there to be an experience. But since experience with no clear utility or evolutionary benefit is so energy costly, it should serve someone else, a spectator or a player. If one day we find a way to simulate conscious beings, the chances we're living in a simulated reality would skyrocket. Physicists at the University of Maryland have already managed to simulate a single helium nucleus, made up of 2 protons and 2 neutrons. And they imagine that if they managed to simulate a nuclear core today, maybe in 20 or 30 years they could simulate a particle. In 50 years, an object the size of a couple of inches. If the advancement continues, it's possible that, decades from now, researchers could reproduce the human mind. The thing is, if we are truly living in a simulation, we aren't programmed to do things because we have free will. Maybe someone wanted to see what we would do with no instructions. And what might happen? Maybe the long years we experience in our world would only be minutes to the maker of the simulation that we're in. Anyway, giving a game character its own consciousness is far beyond any technological advancements we have right now. So, what do you believe? Is the universe and everything not what it seems? Are we living in a simulation? We want to hear what you think, so sound off in the comments, and thanks for watching.